So thank you for your interest in this talk, and thank you to the organizers for the chance to contribute to this interesting series of lectures. So I've given a very broad title here, HyperKähler metrics and symmetries. So this is a big topic, but I want to comment to some aspects of this that are continuing to be developed now. And so the talk is divided into 4 parts. There'll be a general introduction, and then we have a look particularly at dimension 4 and the Gibbons-Hawking construction. Then we'll turn to looking at cotangent bundles, and that will overlap a bit going into talking about co-adjoint orbits, which will be a relatively brief discussion. So let's get some fundamentals in place. So I'm going to be looking at HyperKähler manifolds from the Riemannian point of view. So these are Riemannian manifolds with 3 almost complex structures. So that means I and j and k map the tangent space to itself and square to -1. The HyperKähler condition is that these structures should be parallel for the Levi-Civita connection, and they should anticommute, behaving like imaginary quaternions. So there are some nice direct consequences of this. It turns out the I, j, and k each individually come from complex coordinates, so they're integrable. And the 2 forms you get by putting I or j or k into the metric, they give you symplectic forms. So in particular, these are non-degenerate and closed. So this immediately gives many relationships between HyperKähler geometry and other geometries. I've taken a small sample here in this diagram. So if we focus on one complex structure I, then we can take the other 2 symplectic structures, omega j and I omega and omega k, and put them together in a complex combination to get a complex symplectic form, which are usually called omega c. So in this way, we at least see ourselves as a subset of some complex geometry in general. So this omega c, if I raise it to an appropriate power, then it becomes a complex volume form on the manifold. So what we also have in this situation is that the geometry is a special case of Calabi-Yau geometry, so holonomy contained in SU2n. And Calabi-Yau geometry is well known. Those are examples of Ricci flat metrics. So in particular, HyperKähler manifolds are Ricci flat. So looking in the other direction, away from complex geometry, but towards the symplectic structures, then we have a triple of symplectic forms. And so there are various generalizations of that, versions of that to give you various different ideas called trisymplectic geometry. And of course, focusing on one of those will put you in the case of symplectic geometry in general. And then finally, the bottom line you should take with a pinch of salt, but in the immediate way one defines things anyway, then HyperKähler manifolds are contained in the wider class of quaternionic Kähler manifolds. And these are Einstein geometries. I say with a pinch of salt here because usually in the quaternionic Kähler case you exclude the Ricci flat situation. So to exclude HyperKähler from that. So, but in principle, you can think of HyperKähler as a specialization or a special case of the quaternionic Kähler, but where the scalar curvature is 0. So HyperKähler geometry having all these properties and being Ricci flat and so on makes it fairly rigid as a geometry. But despite that, there are a surprising number of constructions from and ideas from symplectic geometry that go through in the HyperKähler case. So that is partly a theme of this talk. And one reason that these symplectic constructions can go through is that if you just take non-degenerate two forms that satisfy the outer break conditions that come from up here, from the beginning, then the only condition you have to imply on them is that they're closed and give you symplectic structures to get a HyperKähler metric. So this proof you can find several places, but one place is in the book of Vertier and Hitchin. So I've mentioned HyperKähler geometries based on the quaternions. To be concrete, the quaternions are R4, which you think of as being an algebra with basis, the standard basis vectors being labeled as 1, I, j, and k. 1 is central, and the I, j, and k square to -1, and I, j times j is equal to k, and that's equal to minus j times I. So that gives you the quaternion division algebra, and from that we get the simplest example of a HyperKähler metric, the flat example. So you just take the n-dimensional module over H, think of it as a right module for the action of the quaternions. That gives you almost complex structures, I, j, and k, which are actually integrable. And if they are compatible with the standard inner product, and give a HyperKähler structure that way. So there are various symmetries of this this module Hn. We have that the I, j, and k linear combinations of those of length 1. They generate a copy of SU2, or give you a copy of SU2. Or the other name for this is the quaternion unitary group of rank 1, SP1. So we let this act on the right. Actually, every single element in this group is a complex structure on Hn. So you have a whole two-sphere of complex structures. So centralizing this subgroup, this group SP1 acting on Hn, we can think of it acting, it acts by isometries. We can think of it acting as a subgroup of SO4n. So we're centralizing that is the quaternion unitary group of rank n, so SPn. And another way to state the definition of HyperKähler is to say it's a Riemannian 4n manifold with the holonomy contained in SPn. So in this way, this is an important family in Berger's holonomy classification. So I want to talk about symmetries, so let's have a couple of remarks about killing vector fields. So if you have a general HyperKähler manifold, then for a killing vector field, its covariant derivative normalizes the holonomy algebra. So in particular, this killing vector field has to lie in SPn plus SP1. So the SP1 part of this covariant derivative is easy to identify. It's just what the induced action is on the three-dimensional space spanned by omega I, omega j, and omega k, the three symplectic forms. So this action is isometric there and so on. So there are only really two cases of these types of actions. There's either the case where two forms are preserved individually, so the action on this space is trivial, or there is the case where one direction is preserved and X generates a circle action rotating the other directions. So exactly because of what I mentioned earlier, these ABC combinations of I, J, and K still give you compatible complex structures, then you can always relabel your geometry. So in the rotating case, so you have that omega I is preserved by X. Good. So using symmetries, we can think about quotients and so on. So the first remark is that we should be working in the non-compact case in general. So in general, if you have a killing vector field on a Riemannian manifold, then you can compute the second covariant derivative via the curvature. The formula is such that if the Ricci curvature is 0, that implies that the vector field is harmonic. So if you're on a compact manifold, then killing vector fields are necessarily parallel, and from holonomic considerations, then we'll split with a flat factor. So usually we want to work in the non-compact case. It may be appropriate to impose a completeness condition instead, but there are quite a number of situations where the non-complete situation is also interesting. So let me focus on this slide on the triholomorphic case. Then X preserves all the symplectic forms, so we can build usual moment maps, at least locally, in the symplectic way. We get 3 of them, one for I, one for J, and one for K. So we combine them into one formula. We'll say that mu is mu I, comma mu J, comma mu K, and d mu is given by X contracted with omega I, X contracted with omega J, X contracted with omega K. So if this is defined globally, then we will say that the killing vector field is tri-Hamiltonian. And more generally, if we have a group action, then it's tri-Hamiltonian if we can construct, if we have such moment maps for all the vector fields generated by the group action, and they combine into an equivariant map, just as in this symplectic case. So the notion of symplectic quotient generalizes also to the hyperkähler case. So this was proved by Hitchin and so on in the 80s. So when you have G acting in a tri-Hamiltonian way, you can form a hyperkähler quotient. What you do is take a level set, for simplicity, the 0 level set of this moment map, and divide out by the action of G. Of course, you need some assumptions on that for that to be the quotient to be a smooth manifold. But what happens in general is that this quotient here is a union of pieces, and each piece is hyperkähler. So it's not quite stratified, but it has a decomposition into hyperkähler pieces with various parts lying in closures of other parts. So there's an open dense set here that is a hyperkähler manifold. Okay, so let's talk about concretely in dimension 4. So a very old example of hyperkähler metrics comes from Gibbons and Hawkins' work on gravitational instantons. Gravitational instantons are Ricci flat and self-dual in dimension 4, and that automatically implies the hyperkähler. So if you want to start getting examples, then one simple thing is to assume you have a symmetry. And if you have a single symmetry, then the metric can always be written in the following form. So let's say the symmetry is generated by a vector field X. Let's put V to be 1 over the length of X squared. Yeah? Then then there's a dual one form to x, let's call it theta, and normalize it so it becomes a connection one form on x, so theta on x is 1. And the rest of the metric is actually given by the moment map. So theta squared term gets multiplied by 1 over v, and the rest of the metric is given by the squares of the components of the moment map multiplied by v. So I've written the components here as x, y, z rather than mu I, mu j, mu k, because you want to think of these as coordinates on R3, at least locally. And then we see that the metric away from the theta directions is conformally equivalent to the flat metric on R3. So you can write down metrics in this form in general. The HyperKähler condition turns out to be a condition working in R3. If you take the curvature of this connection 1 form, then that should be given as minus the Euclidean Hodge dual of dv in R3. So if you differentiate this equation one more time, take the exterior derivative again, then you get that v is a positive harmonic function on an open set in R3. And that positive harmonic function is enough to reconstruct G. Yeah. So you can ask how many of these metrics there are and how you can construct them all. And Roger Belowski came with a nice answer for this in 1999. He put in an assumption that the topology of the manifolds was finite. It turns out that assumption can be removed. So the statement is, if we assume completeness for this 4-dimensional hyperkähler metric, and we assume the action is a circle action, yeah, then the moment map induces a map on the leaf space to R3, and it turns out this map is actually a homeomorphism. So it's actually a diffeomorphism away from fixed points of the circle action. And you can write down the function v that specifies the metrics. So there's an additive constant which has to be positive or 0. And then there are sum of terms corresponding to the fixed points of the circle action, given by a 1 over norm of distance from the images of the fixed points. So the set Q here is a subset of R3. It's just the images of the fixed points under mu of the fixed points in M4. And conversely, any sum of this form actually defines such a complete hyperkähler metric with circle action under the very simple condition that there is just some point P in R3 where it converges. So in Belowski's case, his finite topology condition just gave finitely many fixed points. So there was no convergence criterion, but it turns out this is the general statement. So let me point out some well-known metrics that crop up from this construction in disguise. So I said the first simple example of a hyperkähler metric was just H, which is R4. Yeah? That comes from taking Q to be a single point. We may as well take it to be the origin. We can translate things without changing the metric. And this overall constant C to be 0. So the circle action on R4, if you think of it as C2, where you act diagonally by e to the I theta, e to the minus I theta, has a single fixed point at the origin and preserves hyperkähler metric. Actually, the case when the Q is the empty set and C is positive is also interesting here. That gives you a quotient of R4 by translations in some direction. So quotients by a copy of Z generated by translations. So this is just a flat structure on S1 cross R3. And if you go back to having Q with just 1 point, but let C be positive, then you get another metric on R4. So the number of points in Q determines the topology. You get another metric on R4. This is known as the Taub-Nub metric, and it has the property that lengths of vector fields are bounded as you go to infinity. So it has different asymptotics to the flat metric. So the other concrete case I want to mention is when you take 2 points in R3. So you could take them to be 1 and -1. There's the only parameter really is the distance between them. Then what you get is a metric on the cotangent bundle of CP1. This is known as the Iguchi-Hansen metric, or is an example of a Calabi metric. So there are also examples where Q is infinite. So the first of these was given by Anderson and Kronheimer and Lebrun. So you need to take the points to be fairly well spaced out to make this sum converge. And what they did was take points along the positive x-axis lying at n squared. Yeah. So the sum becomes sum of 1 over n squared. Yeah. So that gives you a complete HyperKähler metric again. And now the second Betti number is actually infinite. And all the cases where Q is infinite, it will be countable and give you metrics of this type. So many of those have been described by Goto and Hattori. So let me mention something about the rough idea of proof, which is very Riemannian and rather analytic. So there are 2 ingredients. The first observation is if you hold yourself away from the fixed points, so let's call that subset of M0, then mu gives you a conformal immersion on the leaf space into R3. Yeah. So it's a local diffeomorphism. Yeah. And the metric in front of the on the horizontal directions there is, on the leaf space there is this v dx squared plus dy squared plus dz squared. So it's a conformal map. And if you compute the scalar curvature, you get something that's non-negative. So we've thrown away the fixed points, but you can adjust the geometry around the fixed points and still preserve this conformally flat property and the non-negative scalar curvature to get a complete metric. And then there's a rather deep result of Schoen and Yau you can apply to deduce that mu is actually an injective map. So it's a purely Riemannian result of Schoen and Yau about conformally flat metrics with non-negative scalar curvature. So you get that mu is injective, so it maps into an open set in R3, and you can actually control the size of the boundary. The technical statement is it has Newtonian capacity 0. That means bounded harmonic functions extend across the boundary. So then you need to use some potential theory. So harmonic analysis in R3. So what turns out to work in the infinite case is to use the Martin boundary representation of positive harmonic functions to get growth conditions on the V. And then you can put those into estimates from the completeness condition you have on your metric to show that this boundary of the image is actually empty. So so in this set, I'm including the images of the fixed points, so those are allowed to be there. But I mean the remaining part of the boundary is empty. So you get the boundary of this is empty, so the image has to be the whole of R3. So that feels like a very indirect way to prove these statements uses some very general Riemannian results that are rather deep. And after the first line or so of the construction, which is really the Gibbons-Hawkins input, there's not really much hyperkähler input in this proof. So it's a very natural question to ask whether there's a direct proof of the statements above that are used. So in particular, that when we restrict take the map mu on the leaf space, that it is injective, or actually it would be enough to just think about to prove directly it was surjective. So it would be very nice if there was some direct hyperkähler way to use this to get such a result. So this is relevant, the four-dimensional case here is relevant for the general toric hyperkähler picture. And it has relevance for other toric considerations of moment maps and so on. So for other holonomies. So let me change direction, and we've already seen that the cotangent bundle of CP1 is a hyperkähler metric. It was given by one of these Gibbons-Hawkins metrics. Yeah. But you can ask in general whether cotangent bundles carry hyperkähler metrics. So that's a sensible question, because whenever you have a complex manifold, then the cotangent bundle naturally carries a complex symplectic structure in exactly the same way as the cotangent bundle of a real manifold carries a symplectic form. So you can then ask whether there is a compatible hyperkähler structure. And there are at least 3 different situations where there's a positive answer. So the most general result is the following one of Fikes and Kaledin. So in this case, you assume that N is real analytic and Kähler. Yeah. And then you can prove that a neighborhood of the zero section of in the cotangent bundle emits a hyperkähler metric that's compatible with the standard complex symplectic form. So this construction is a generalization of the Grauert tube construction of Kähler metrics on tangent bundles or cotangent bundles of Riemannian manifolds, real analytic Riemannian manifolds. So it's not an explicit construction. It's hard to understand what this metric is in general. But this metric has a characterization, at least. So it has the property that when you restrict it to the zero section, then it gives the original Kähler structure on N. And if you look at the circle action, that is multiplication in the fiber, so rotating the complex symplectic form, yeah, then this is actually an isometry of the hyperkähler metric and it's an isometry of the rotating type. So in general, the matrix constructed here is not complete, but you can, in different situations, you can study completions and you can control the completeness in some situations. So there are several different papers that deal with different cases. There's a fairly recent preprint of Abasheva that does a certain class. So that's a very general result. I said I wanted to give 3 results. Well, the second one is almost completely at the opposite extreme. So if you take a Hermitian manifold, then and equip it with a connection, and I'm not initially going to assume this connection is compatible with anything much of the Hermitian structure. Then a connection gives you a way to split the tangent bundle of the cotangent bundle, and then you can use the into a copy of the tangent bundle and a copy of the cotangent bundle itself. And then on each of those, you've got a 2-form given by the 2 form from this Hermitian structure. So you can combine those and try to call that omega I. So then it's natural to ask whether you can put this together with omega C and get a hyperkähler metric. And the answer is yes, in some circumstances, if you need strong compatibility between the Hermitian structure and the connection. So I think the first exposition of this you'll find is in Fried's paper from 1999, but there are many other people who have written descriptions of this construction. So, so this pair defines a hyperkähler structure on the cotangent bundle, if and only if the base manifold and connection form what is known as a special Kähler structure. So here special Kähler means that the connection we have is flat, it's torsion-free, and it's symplectic. So the symplectic form is parallel. And there's an extra condition, which is that the covariant derivative of the complex structure should be symmetric with respect to x and y. So that's a very strong type of geometry. But there are a number of constructions for physics of these things. They're given by a lot of examples, and so a lot of this comes from the supergravity literature, and there are ways of constructing these from homogeneous cubic polynomials, for example. So you can get some extra symmetry in this situation, which is useful for some of our considerations. So there's a subclass of these special Kähler things that are called conic. So this means they have some sort of cone structure. So you have some scaling, you have some rotation. The rotation is generated by a vector field x, and the covariant derivative of x with respect to this special connection and with respect to the Levi-Civita connection should give you minus the complex structure you're working with. Then it turns out that I times x is actually a homothéty of the metric, so you really get something that looks like a cone. So in this situation, the vector field x, you can lift it horizontally to the cotangent bundle, and that actually preserves this type of hyperkähler structure as well. So you get a symmetry, and it's a symmetry of a rotating type again. So this is not the symmetry we're considering in the Fikes-Kaledin construction, but this symmetry is given by horizontal lift of this conic symmetry. So why are we interested in, might be interested in rotating structures? There's a general construction called now known as the quaternion-Kähler hyperkähler correspondence. And essentially this comes from some T-duality. The way I want to present it here, I want to use a geometric version of T-duality I call the twist construction. So the twist construction should start with some manifold M that carries a circle action. Above that you should have a circle bundle, a principal circle bundle, whose curvature is preserved by the circle action on M. And then what the twist does essentially is that you lift the circle action on M to the principal bundle. There are different ways to do that. You can take a horizontal lift of the vector field and then combine it with some function times the principal action. And then you take look at the quotient by this new vector field and build a new manifold, which are Q in this case. So that's a very general topological construction, going up to a circle bundle and taking a one-dimensional quotient again. You can, the P, if you, to lift horizontally, I had a connection on P. You can use that to lift any metric on, you can look at any pullback of a metric on M and restrict it to the horizontal distribution you get from that. And then you can push that down again with Q. So you can push things like metrics and so on through this construction. So in the hyperkähler case, this turns out to, the way to think about this turns out to be as follows. So we want the M, I wanted some circle action length. So let's take an X that is of rotating type. And let's assume there's a moment map for the Kähler structure it preserves. Then I said P had to be an S1 bundle over M with connection. The principal action is generated by some vector field Y. I'm going to call H the horizontal space. And it turns out that we need this to have a particular curvature for what I want to do. So the curvature form should be the differential of the metric dual of X plus the Kähler form that X preserves. Then you construct Q as the quotient of P by the horizontal lift at X plus A times Y, where A is this peculiar function, norm of X squared minus mu I plus a constant. And you find that the Q you get out of this is quaternion-Kähler with an isometry. So the Y vector field is now transverse to the vector field we quotiented by to get Q, so it induces an action on the base. But there's a slight catch in this construction. The metric you have to put on Q comes not from the metric you started with on M, but it comes from what you might call what I call an elementary deformation of that metric. So it's almost a conformal rescaling of the metric, but you have to use different conformal factors in the direction that generate it spanned by X, and the direction is orthogonal to X. So it's an elementary deformation of this metric here. And what you take a conformal scaling of the hyperkähler metric here by moment map shifted by a constant. And then if you look at the metric restricted to the four directions, quaternion directions spanned by X. So there's X and there's IX, JX, and KX. That's a four-dimensional space. You need to scale that by the factor given here. So that looks very specific in the way I've set it up. It comes from a result of Hades in the first instance, where he went the other way around. He started with a quaternion-Kähler metric and showed how to construct a hyperkähler metric with a rotating circle action. So Hades's work immediately tells you every quaternion-Kähler metric will arise in this way. So it turns out that this elementary deformation formalism is exactly how you get to the hyperkähler metric. And using this twist construction in general and starting with an arbitrary hyperkähler M with rotating X and an arbitrary bundle P, and just considering which elementary deformations, considering arbitrary elementary deformations, then together with Oscar Marcia, we managed to prove that this is the only way to get quaternion-Kähler metrics out of such a construction. So why is this useful? So quaternion-Kähler metrics are quite a bit harder to work with in hyperkähler. They don't have symplectic forms, and you can't use techniques from Kähler geometry and so on in such an easy way. On the other hand, they're nice, interesting examples of Einstein metrics, and they belong to the Berger classification. So if you can use some, if you have some other geometries that are easier to work with to describe them, then that's a useful technique in general. So this is one of a couple of different ways that hyperkähler geometries are related to quaternion-Kähler. But one thing you should notice about this is that when you do this elementary deformation, so what do? We take the original metric, but we change it by a different factor in directions along x and this quaternionic span. Then actually the metrics, if you want to get a positive definite quaternionic-Kähler metric out, then the HyperKähler metric you need to work with is often of indefinite signature. So often to get a 4n, 0 metric out, you need to start with a 4n minus 4, 4 metric. So this correspondence is a mathematical version of some constructions from physics and supergravity literature. So there's something called the C-map and so on. And in the physics literature, it's been known, there's been local descriptions of these metrics, at least known for a long time. And it's a very powerful construction. So it actually produces all the known left invariant quaternionic-Kähler structures on Lie groups. So these turn out to be quaternionic-Kähler metrics of negative scalar curvature. You exactly have to go via HyperKähler metrics that have indefinite signature. So in fact, you look at cones of special Kähler manifolds that have signature 2n, 2. Those can be thought of as fibering over a positive definite Kähler manifold. And so de Wit and Van Proyen were, from the physics side, first gave some concrete information in this direction. There's earlier work of Chicotti and Ferrara and so on. But the de Wit and Van Proyen work was remarkable because it actually showed that the original classification that Alexievsky had given of quaternionic-Kähler structures on completely solvable groups was missing one family. And Cortés in '96 showed how to correct Alexievsky's construction and produce that family as well. So Cortés has worked on in this area a lot since then, using many results. There have become more and more mathematical descriptions of the whole process and different aspects of this process. And in particular, Cortés and co-workers have produced several other complete quaternionic-Kähler manifolds this way, including examples of lower homogeneity and various flavors of classification results. But it still remains open that the general question of classifying quaternionic-Kähler metrics on homogeneous spaces and on Lie groups. This is a special case of the Alexievsky conjecture. But in the quaternionic-Kähler case, there are a number of other tools such as this that you might be able to use. So one problem is natural to ask is, can you use this QK-HK correspondent to actually get a full classification of the homogeneous quaternionic-Kähler manifolds, or at least get more information about how the structure of those manifolds? So it's not even a priori clear that you should just be restricting to HyperKähler manifolds here that come from special Kähler geometries. It could be more general than that. Okay, so the last part of the talk, I want to move to co-adjoint orbits. And I have not counted wrong about how many cases of tangent bundles I'm talking about. So there's some overlap here with cotangent bundles. So the original non-trivial complete example of a HyperKähler metric is due to Calabi. It's on the cotangent bundle of CPN. And the modern way to construct that metric is the HyperKähler quotient of a circle acting on, I guess I should write HM plus 1 here. Yeah. So So if you let a circle act essentially as a diagonal element in SPn, then you just multiply each quaternion coordinate by e to the I theta. Then the HyperKähler moment map is given on Z plus JW with Z and J in Cn by the difference of the lengths of Z and W squared in the real part, and then there's the complex part can be combined to be just the product. So that should be a Z transpose W of Z and W. So so you can get the cotangent bundle that way. But you can also think about the cotangent bundle in a different way. You can think about it as you can give different homogeneous descriptions of it, and you can think of it as an orbit and appropriate representations. So one presentation is to think of it as an orbit under the adjoint action of SLN plus 1C in SLN plus 1C of the matrix I've written down there, or any other scalar matrix of that form. So there's a free parameter in the Calabi metric. So SLN plus 1C is acting on this by conjugation. So the killing form of SLN plus 1C is non-degenerate. So you could alternatively identify this as an orbit in the dual space, and then you're looking at co-adjoint orbits. And co-adjoint orbits, they're good examples of objects with symplectic or complex symplectic structures. So if you take any Lie group over the complex numbers, then every co-adjoint orbit emits a complex symplectic form due to Kirillov, constant, and Suryaw. So if you take two tangent vectors generated by the algebra elements A and B, and you're at some linear form phi, then omega c at that point is just phi evaluated on the Lie bracket of A and B. So that is actually a genuine complex symplectic form on any co-adjoint orbit. So if you assume G is compact, then there's a very nice result, which was initially proved for nilpotent orbits and semi-simple orbits by Kronheimer, but the general statement was given by Bikar and Kovalev. So for compact G, you may as well take it to be semi-simple here because the center is going to act trivially anyway. Then every GC orbit in the dual space, every co-adjoint orbit carries a HyperKähler metric compatible with this Kirillov constant Suryaw form, and this metric is invariant under the compact group. So I've already pointed out that there are a couple of cotangent bundles hiding here. There's also some cotangent bundles that are not hiding here. There's a related result of Kronheimer, which says that if you take the cotangent bundle of the complexification of a compact group, then that also carries a G-invariant HyperKähler metric, at least in a certain neighborhood of the zero section. So these two results have a very common flavor. So the construction is based on realizing these orbits or cotangent bundles as moduli spaces of solutions to NARMS equations. So NARMS equations are given equations on three functions defined on some interval in the real line, mapping into G, into the Lie algebra. And they take the form that the derivative of one function is given by the Lie bracket of the other two. So exactly which interval you take and what boundary conditions you impose give you give you different examples as above. But what is common to this is that you can regard this as you can regard these equations as a hyperkähler moment map on some infinite dimensional flat hyperkähler space. So that is essentially what gives you the hyperkähler structure on the quotient spaces. So this is an infinite dimensional hyperkähler quotient that's being used. Of course, you need to do quite a bit of analysis to make sure that works in the way you want to. Compactness of G is very useful there. It's not completely essential. You can do various things for reductive G as well. But in many ways, this is a very abstract construction. It's not always clear what metrics you're going to get. So a nice general problem is to give some more direct and finite descriptions of these metrics. So what I mean by this is varies a bit from situation to situation. One way to approach it is that hyperkähler metrics are Kähler. So you could ask to write down explicit Kähler potentials. And if the cohomogeneity of the metric is quite low, then there aren't many free parameters, and it's quite often you can solve explicitly for the Kähler potentials. So, so there are papers covering cohomogeneity 1, 2, and 3 at least. Another direct construction is the finite dimensional hyperkähler quotient. Yeah. So I already told you that the cotangent bundle of CPn can be achieved that way. For SLN C, you can actually get all the orbits as finite dimensional quotients. So what you want to do is consider a big flat space, which is the vector space of all the complex linear maps between these spaces I've written down. So this is an example of a quiver, a vector space coming from a quiver. Quiver construction. There are many different quiver constructions and so on. And but let me focus on this one. So you take the full flag on Cn, and you look at the maps that go up and down between successive spaces. So if you do that, then there is the group, the unitary groups on each factor act. You want an object at the end which is an orbit for the complex group SLN C. So you shouldn't quotient out by that, but you can quotient out by all the other ones. So you take the product U1, U2 up to UN-1 that acts on these spaces, then so it acts on the maps as well and gives you a hyperkähler action on HN. And then you can take, you can build the moment map, and you can take quotients. So there are some constants you can add into the moment map corresponding to the center. So essentially there are n-1 constants you can add, one for each circle in the center of ZG. But they become they become complex constants. And that's actually enough freedom to actually hit or give you all the orbits of SLN C, or at least all the orbit closures. So for example, if you take the standard map, take it at level 0, then you get the whole nilpotent variety, so all the nilpotent orbits as one big union. You can get individual orbits by throwing away some bits of the construction. So that's a very satisfactory situation for SLN C. It turns out there are some similar constructions for other classical groups, but there the center is a lot smaller, and essentially you get nilpotent orbits and a few other orbits, but nothing else, but not the whole picture. So we're missing constructions like this that give you other orbits in classical groups, and we have no construction at all when the group is exceptional. So G2, E6, E7, E8, and F4. Yeah. So those are all legitimate objects. There really ought to be nice finite dimensional considerations like this for those as well. And it will be even better if there was a nice finite dimensional construction like this for the other classical groups, where you had a big center where you could vary the parameters. So let me pose a couple of problems here. So everything I've given on the previous couple of slides was really for G compact. You can relax it to G reductive, but these co-adjoint orbits, they exist with a complex symplectic structure for non-reductive G as well. So it's a nice question whether you can find hyperkähler metrics on those orbits. That's almost certainly too much to ask for. When you go to other non-compact real forms of reductive groups, then the hyperkähler metrics you construct usually are just defined on open sets of the space you're interested in. But you might get around it by allowing hyperkähler metrics of non-positive, non-definite signature. And maybe even better, you can get away by looking at metrics that are allowed to degenerate along hypersurfaces and so on. So there are notions of things like folded hyperkähler structures, and in the Gibbons-Hawking construction, for example, you can take this C parameter and make that negative, and those give you different ways of getting hyperkähler metrics that change their signature when you pass along some hypersurface. So why are these things interesting? Well, if you have hyperkähler structures on orbits, then it widens the applicability of the hyperkähler quotient construction. So in symplectic geometry, you can take symplectic quotients at levels that correspond to elements in the center of the algebra, but you can also, using co-adjoint orbits, you can also take quotients at levels corresponding to other values in the Lie group, in the dual of the Lie algebra. So what you have to do is take the pre-image of orbits of co-adjoint orbits, and then take the quotients of those by the group. So you would expect to be able to, if you have a hyperkähler metric on such orbits, then you can use such an idea to construct hyperkähler quotients at other levels. So this is very useful when G has a very small center. Yeah? So groups like SU2 and so on, they don't have much of a center, so there's in the first instance, there aren't many hyperkähler quotients of them, but if you use orbits in this way, then you can construct other hyperkähler manifolds. And well, for the compact G, we have the constructions of the previous slide, so we can do that. For non-compact G, then we don't have an answer at all to the problem above. So we don't know whether we can do this. So one of the reasons I include this here is there's a reasonable amount of recent work on non-reductive versions of geometric invariant theory. So a lot of the ways you want to think about these things is to pass to the complexify group action and just look at GIT quotients with respect to the complex group. Yeah? And there's a better and better understanding of situations you can do that in now. So I've given a couple of references at the bottom there, but there are plenty of other authors that have worked on these things. So that might be one way to tackle this. Another way is just to go away and look at small dimensions and so on and try to deal with particular cases. I don't think anyone has really done that systematically. There's been some work, but there's not really systematic. So this is essentially where I will stop. I will just let the list of references go past in the next few minutes. Thank you.